So thank you all for your patience. My name is Tobias Fuchs. I am currently working at LMU, Ludwig-Maximilians-Universität of Munich, following my PhD in high-performance computing. I'm programming in C++ for about 15 years. 7 of those, I did a really bad job in this. Then it took like 3 years to realize that I was bad at it, and now I'm in the progressive, on the right path, so to say. High-performance computing. So a year ago, I wouldn't have planned to give this talk because I wouldn't even think that those problems exist, but actually they do. So just to get you guys a bit to know a bit better, who of you guys is in HPC, so in high-performance computing? Okay. So in this case, my introduction slides are not wasted. And does anyone in here know what a monoid is? Very good. This talk is not for you, but but you'll see what I mean. So what's the problem in high-performance computing? So not too long ago, data centers looked like this. And everyone was proud of it, and this is actually where the name tape archive comes from. So TAR is for tape archive, those tapes. And all the problems we have in HPC right now come from the fact that nowadays data centers look like this. Same company, different configuration. And a lot has changed in terms of hardware and software abstractions. And I'll just give a really brief wrap-up of the chronological changes in high-performance computing. So first, we had this one huge mainframe. So like those big old trays that looked really fashionable, that had one core and working memory, and perhaps some tape archive. And we just increased clock frequency because there was lots of space between those transistors. And then this space ran out, and all we could do is add more cores. And even then, we had the next bottleneck, which was the L3 interconnect, so we had to add sockets. And even this wasn't enough, because now we have special purpose accelerators like GPUs or Xeon Phis. And even this is not enough nowadays. We also have heterogeneous nodes that also involve, say, digital signal processing accelerators, GPUs, and Xeon Phis on the same machine. And this is already the reality in embedded systems, actually. So who of you is working with embedded systems? Yeah, I suppose so, quite a bit. So there are many architectures that are really heterogeneous, even on chip. So everything I'm telling here will someday it will affect you. So we have a machine like this, and the actual idea is we have more memory, so we have more RAM, which is heterogeneous. So that is to say, the access from one domain to another is non-uniform. And also we have cores, that is to say, computational units that have different capabilities, like SIMD width or cache sizes. So in an HPC cluster, this gets even worse because we also have the network interconnect. And this gets worse and worse. And if you have a really deep hierarchy and it's heterogeneous, that is to say, in this case, we have 4 CPU architectures. And when you consider, say, this as like a huge flat, and you want to move IKEA furniture from, say, this room to this room, and from this room to this room at the same time. Well, there is some sweet spot. Say, when 4 people are helping, it's okay. When 4,096 people are helping, it will be a bit messy. And this is exactly what we do in HPC. So this is a rough wrap-up of the problems we have in general. And a typical application we run on those machines is, for example, a stencil. This is a really simple stencil. So we have a 2-dimensional image, pretty simple, and we run a Gaussian blur filter on it. It's really simple. It's just you have one cell, and in every step, so you have back and the front buffer, and the front buffer you just take 0.0 times the value in this cell plus 0.0 in this cell, etc., and you just add it up. And this is the kernel that you call for every cell. And already here we see that there is index calculations involved that actually have meaning. So cell at index ij, this is the current cell, this would be the center. ij minus 1 would be west. And already there you perhaps need some nodes when you're programming just to see, okay, which is the first dimension again. And so you run this stencil, so for every single cell. And suddenly you have a problem because the actual image is distributed over the whole cluster. So this is already a problem with new architectures. So when you say the left part is allocated on one NUMA domain and the right part on another, but just assume that there is an InfiniBand interconnect in between. So some gigabit Ethernet. So to access this element, to update this cell is really, really expensive. So you don't do that, because you would have to do this for every cell here. And of course, this is two-dimensional, so you have neighbors here and here. And this is really, really expensive. So it would be communication bound, and actually it should be a computation bound problem. So what do you do? Well, you just copy the neighbor cells. So in every step, you copy all those, we call it halo cells or ghost cells, just depending on the direction you're looking from. So at the beginning, we copy all of those in one contiguous memory chunk, and then we can access it in the local memory of the process. And of course, then in the next step, process B will have updated the cells, so you have to copy them again. But it's better to copy all those elements in one communication call than to access every single element and stress the hell out of the bus. So this is where index sets come into play. Because actually, you have an index for, so a canonical index, we call it, just the logical enumeration of the cells in the image. So this is one index set. And of course, you have it in all of those partitions. And then you have an index set here that enumerates exactly the halo boundary, so the boundary elements that are also mapped here. So we have a mapping. That is to say, index 0 in our buffer maps to index 0 in process B, index 1 maps to 8, etc. Not too much fun. So, can it get worse? Oh, yes. So first, to wrap up the actual problem of data access in HPC. So this is the data access in HPC. That's it. You can reduce the number of communication accesses. So just access less elements. Or in this case, just copy a contiguous chunk of memory instead of every single element. So instead of 8 single accesses, you have one copy command. You can replicate data ranges. So this is actually what we did here, but you could also say a partition of a graph, and you assume that it won't change in the next iteration. There are many, many strategies. You can improve the surface to volume ratio. Anyone heard of that one? Surface to volume is really easy. So this is a square, and it's just the surface of the square is exactly the boundary elements. And the volume of the square, because we are in 2 dimensions, is, well, the actual surface. So 8 times 8 elements. And the ratio just determines how many boundary elements are there for in relation to the actual data in the cell. And of course, want to optimize it. So assume this would be a 2x 64 a 2x64 partition. Then of course everything would be a boundary. And then we can reduce the access distance, so we can just communicate. So processes that are presumably cooperating in the application, we can pin them close to each other in the machine topology. So I work at Dash, which is a C++ library that aims at establishing something like an STL replacement for HPC. So the core principle of Dash is a partitioned global address space. So what's partitioned global address space? So virtual address space is pretty much clear. So there is an address space, but it's actually just logical. It's not actually the physical memory, and you access virtual memory, and then you have a redirection and translation look aside and whatnot, and then you have access to the actual physical memory. And this is exactly what we do with distributed memory. So let's see what we do. Say we want to distribute an array, so one-dimensional sequence with a fixed size, and just imagine this 40 is a stand-in for a really, really huge number, like 40 gigabyte or something. And we want to distribute it on this machine. So what this does would be this. So we have a concept that's called a unit. A unit is just a generalization of threads, warps, processors. So any programmatic concept that has computational capabilities and memory in some respect. So it could be a warp in a GPU, a thread. It could not be a SIMD command because those again can't involve memory. So you need so anything that has something like an instruction buffer and a data buffer. So and we partition this array in a fashion that, so in this case, if you don't specify anything else, it would just partition those elements in a blocking fashion. So it would balance the elements among all those units. And in this case, those white circles are a pinned process. So one process occupies, for example, this core and this NUMA domain, and it would be assigned to this part of the array. And we, of course, in virtual memory, you have virtual addresses, and also for the same reason, we need global pointers, which is just a virtual pointer on global memory. So it's pretty simple. You have a segment, a unit, and local offset. Segment is just every allocation unit. So every time you call a global malloc, you get a new segment ID. The actual interesting part is you have a unit and a local offset. So, for example, this element could be unit 0 offset 2. Easy. And this is how you access it. So we mimic STL, so C++ standard template library concepts, because they for one thing, they work and they are known. So we try to reinvent and circumvent as few concepts as possible. In this case, you have to specify, well, the blocking scheme, so the distribution scheme, in this case blocked. And you can just access the array using global indices. And in this case, unit 2 would access, for example, global index 27, and it would redirect to a local access. Accessing array index 35 would be a remote access. Any objections?
Just one question.
Yes?
The concept, I mean, in STD, you have the concept more than arrays contiguous in memory, you have cache mechanisms on the neighborhood. Here, you don't have it?
Yes, you do, but only locally. So this is a bit, local. So the local part of this array is a regular contiguous chunk of memory that is allocated using some underlying substrate like mkmalloc or whatever, so to ensure alignment and so on. So, but the actual problem here is so if you would just, we of course also have global iterators. So if you would pass, say, a STL find, and you would pass a global pointer to an array, it would just do lots of remote accesses, and you wouldn't be any wiser. So it wouldn't be too efficient. So you also need an explicit local access. Yes?
So in this case, in C++, this would go on the stack. And you're probably doing some kind of allocation across machines?
No. The allocation happens at this point. So once the constructor returns, this is a collective operation. So the constructor call is executed by every unit and returned when every unit completed the allocation.
Yeah, right. But so there's no stack here, right? So this obviously
you can't.
This has to come out of some dynamically.
Exactly. Even worse. Even worse, it has to be collectively aligned memory. So this is an MPI specific, perhaps, but it's even worse than dynamic allocation, because it has to be globally coordinated. Absolutely, yeah.
But it doesn't make sense for like stack size thingies. This is used for like.
Exactly. You wouldn't. To put it on a stack, you need an allocation policy. But this is not in this talk. We can talk about this later. But for now, we assume we have this use case where, from the beginning with the two-dimensional stencil, and you need perhaps two of those for back and front buffer, and they live throughout the application. Or for
somewhere as an implicit template argument.
Exactly, absolutely. There's even more fun behind that, but we can look at that later. So for now, okay, we understood. Okay, we need some way to express. Okay, I want a local access. So I don't want to. I know that I'm in this global array, but now I want to address only my local part because I want efficient access. So and array.local or array pipe local, which we'll see later, returns a type that is again a model of array. That is to say, array local again is an array. So you can call begin and end on it, and size, and of course also call the subscript operator. Okay. So in this case, you have this global array, and when you call array.local, you just restrict your index set or index range to this partition. And of course, now you have a local index. So it starts with 0 ends with 10 excluding, while here it was 20 to 30. So we all, yeah.
It's local like an array view. Is it a reference type?
Yeah, it's absolutely an array view. But I didn't mention the term view yet. But yeah, absolutely. But the array view that you're referring to is the STL concept array view, right?
Right.
Conceptually, yes. The implementation is totally different. But we'll come to that later. Okay, so we already have two index domains. We have the global index range from 0 to 40 excluding, and the local from, in this case, so a line from 0 to 10 excluding for every unit. So, I said, okay, we want to be a stand-in replacement for STL. So you just replace sdit or std : with a dash : and it should it should give the same semantics and behaviors as you know from STL. Now let's see what we get with this. So the trivial implementation of a dash for each, for example, is just, well, it's a collective operation. Every unit has to participate in it. And so the programming model is SIMD, so every unit executes exactly the same code. So a really trivial implementation would be to just a dash for each would just call standard for each on the local partition of the array on every unit. Right? So when dash for each returns, every unit completed its the unary operation on its local part of the array. So I said we want the same semantics as we know from the STL. Do we have those? No, we don't. Because standard for each promises that there is an element-wise, so in-order visiting of the elements. We don't have that. We have an in-order iteration of the array elements locally, but not in the global scope. So if we want STL semantics here, we would have to add a barrier and a communication scheme between every one of those consecutive units. So unit 0 would start, and then unit 1 could only begin once unit 0 finished, and this is of course not what you want. Yep. Sorry, once again?
Can the operation carry state?
Sure, why not?
Okay.
It can even have a global state. So we have, do you have an example?
Like if you say it doesn't preserve the order, the only way for me to know is if my operation somehow has state, so that I can compare which elements I already did.
Yeah, exactly. That's perfectly fine. That's possible. I also have some demos for exactly this case. Perhaps I'll have time for that later. So okay, so we just bite the bullet and say no, we have to deviate from the STL semantics a bit because it wouldn't be useful. And if you wanted something like in order, so globally in order iteration, then just do it yourself. Yep.
For example, the new execution policies in like the extension executors, for example, they give a different set of guarantees. And that came after you designed this, or? Okay.
We have those, yes. But they are. I'm not finished with them yet. So I want to mimic STL as closely as possible. But in case of launch async, for example, we can't. But so that's a detail that we can discuss later. But this is just a caveat emptor, just to blame ourselves or ourselves that we cannot do a dash launch async. because the implementation of, so the local implementation of the dash for each or any dash algorithm would have to know that it has been called asynchronously, because it has to use different communications substrates then. But this is just a disclaimer. Let's make it a bit more complicated. So okay, so before we just visited the whole array, right? So we had array begin, array end. What if we just need a subsequence of this array? Already not so much fun. So of course, so we have a global iterator. So we also give an index or an offset in the global index space, unsurprisingly. But this translates to a local index space at some point. And in this case, this unit 0 and unit 3 wouldn't be involved in this operation at all. And unit 1 and 2 would have totally different local index ranges to iterate. So in this case, it's probably pretty easy to translate, right? So you just take the local size, and then you subtract, and then you subtract this from end, but then you have to, well, you just watch out for those off by ones, and yeah, you know the drill. And this is what we do. So this is what this talk is about. What we actually want is, I want to say I have an array, and I use this sub operation that perhaps some of you know from Eric Niebler's range proposal. So this has the same semantics as your good old pipe in the shell. So from this, I want a subrange, and from this subrange, I want the local part. And this gives a different result depending on the unit. So yellow is unit 0, so unit 1. Unit 1 would have index range 2 to 10, and unit 2 0 to 8, and all other units would have an empty range. It could just return or block or whatever they deem useful. So okay, this is what this talk is about. And as you can see, this translation then is trivial. You just have the local range begin end and do the same as before. And this is exactly how dash for each is implemented at the moment. So I already mentioned Eric Niebler's range v3. Just a quick hands up, who knows about the range proposal? Awesome, awesome, awesome. This saves so much. Huh?
The proposal is not a range like this.
It is not exactly.
No, exactly. Like you use all the nice algorithms. Because you can't pass range, you can't pass iterators to the algorithms anymore. I mean, like you don't even get the pipe operation.
In range, range v3 has make pipeable.
Yes, but that's not a proposal. Proposal is just like.
I'm sorry. Yeah, but there is range v3 is a reference implementation that goes way beyond the concepts in the proposal. Absolutely. But yes, there is still. I just assume that range v3 is more commonly known than the SDL proposal. Okay, so why don't we just use range v3 then when it's already there? Yeah, because well, the range proposal has some nice propositions, but they don't fit our needs. We have domain-specific needs, pun intended. So there's some mappings that we have to say reapply, rollback, modify, and reapply. And this is exactly what ranges in the proposal don't. If you are familiar with them, you will see what I mean. So, for example, how does a view in a pguess container work? Well, in this case, this is what you get from the array sub. This is what you get from when you apply local to it. Then you can apply index to it, which would yield for unit 2, 0 to 8. Then you can apply global to it, which would again return the global index of this local index. And I'm trying hard to avoid any terms ending in morphism. But so if you are into category theory and set mappings, you see why this is useful and why ranges can't do that. Okay, more complicated example. So we had dash for each. How about copy? I have two arrays distributed in the same fashion, just to make things easier. And I want to copy a subrange from one array to the subrange of another array, or perhaps the same. Okay, so we talked about communication avoidance or optimized communication schemes earlier. So yes, you could, of course, And this actually works. You can call standard copy and just pass it array begin, array end, or array begin plus something, and it would work. Because we satisfy all STL concepts, it would compile and it would also do it would also have the expected behavior. But it would, of course, be slow as hell, because standard copy doesn't know of communication optimization schemes. It would just copy element by element. So what do we have to do? Actually, we have to match subranges. So the first subrange here is limited by the target subrange, which is in this case shorter than this one. Then it has to switch targets. So now this part goes to the next unit, and this one to the end of this unit. And all of those copy operations could happen in parallel, or asynchronously, or whatever. And with views, so when you have this the view extensions in Dash that are not merged to development yet, I'm working on it. It's the gist of the algorithm pretty much boils down to this. So I have a subrange in the source, I have a subrange in destination, and now I want the intersection. So can I do a local copy? In this case, this is deceiving because it just looks like you could copy this to this range. Well, both are local, so both on the same unit. Yeah, but the target is different. Target is over here. And so at least my students really really have a hard time with just calculating this linear index ranges. And then of course you always have those off by ones. Okay, so once you have it,
No, off by ones. I love them.
Yeah. Now, apart from programming courses, I wouldn't know why I would. Yeah. Which index calculations did we actually need for this copy operation? Did we have to calculate every single index of every element? No. We just needed for every block, that for every contiguous block we operate on, we needed the begin and size or begin and end. So actually, some overhead would be okay. Let's see if we have some. So how do we implement that? So now you see what it did for one dimension. Now I'll just show you the real brief, the formal approach or ideas behind it. If it's getting too mathy, just throw a beer bottle or something, or yell boring or whatever. I try to keep it short. So you all know the basic set mapping terminology. So you have an elements in a set from a domain, and you have a mapping or a function, and it transposes, it maps elements from the domain to the image. It looks like this. So this element is not mapped, and that's not a problem, because you don't have to map every element. And then you remember perhaps those injective, bijective, surjective thingies that I will try to avoid. In our case, we have a bidirectional mapping from origin to view. So view is our image. It doesn't actually own elements. This is exactly what we have for array views or for the STL views you already know. So views don't own anything. And for that reason, their lifetime depends on the container. So once the container is deallocated, the view doesn't point to anything. We have a bidirectional mapping. Well, this is unsurprising. So we also call this a well-defined mapping. And the origin, so this is Dash terminology. We call it origin. Origin is the domain that actually owns those elements. And of course, between origin and view, there could be many domains that again are a composition of views, etc. I try to keep it short. And in our case, we have a view that is really dumb. Views don't know jack. Views have a name, and they don't even know what their name means. Views have no concept of their own operation. What they do have is an index set. And an index is just a mapping from a sequential range of indices to indices in the origin. Okay, so we have the view index space. This could be local, sub, whatnot, whatever views do. And the canonical index space, and this is, for example, the global array index. Code, finally. So this is a drastic oversimplification of the actual implementation, but just to show the basic idea behind it. So a view is a mapping from a domain based on an index. Sure. And this mapping, well, you have, for example, the subscript operator expecting an index. And whenever the view has to access its elements, it doesn't own them, so it has to pretty much redirect them from its domain and apply its index. So you have a simple arithmetic interaction in between. And a view also doesn't know about its size. A view just asks its index about its size. And this is a simplification of the constructor. So a subview, for example, would expect a domain, for example, the global array. Then int A and B, this is the subrange, and initialize the index from the domain's index and IAAB, which looks like this. Unsurprising, a view again, an index again, doesn't really own anything. There is a reason why I have this unspecified member type, because, well, if you write those pipe operations right after each other, right after another, you want to move those through the whole pipe, of course. And if you store a pipe operation in a temporary, then you want a const reference. So this is just nods toward the perfect forwarding member scheme. So, and again, what does an index do? Well, an index itself returns its offset. So in this case, we have sub. So when we have sub with 10, 20, from 10 to 20, then every access to index 0 would be translated to an access to index 10. So it would just add IA, so the first index. And the size is just, so there is no bounds checking here, but you know the drill, so it's just end minus begin, and that's the size of the index. And now you just have to imagine there's lots of const expr and lots of specializations and lots of spinae, but that's the overall gist. So that's how it's implemented. Just a comparison. So this is this example from sub local. So take the local part of a global subrange. This is an implementation we had before in Dash. And we had lots of specializations. So we spinite the hell out of this. And so this is not overly tuned, but we tuned it until it matched or overmatched our competition, which is UP, C++, Chapel, etc. And then we just didn't optimize anymore because, well, good enough. Okay, so this is just one specialization, just to give you an idea what the code looked like before. And this is what the code looks like now. With the nice addition that it also works for multidimensional ranges, or in formal terms, for anything that can represent an n-dimensional rectangle. And for one dimension, this rectangle would be a sequence. Nice. And now the only task left is to convince people to use this, or to convince them that this isn't just some formal trick. So this is a mascot I invented. This is Fritz, the Fortran fanboy. Well, the Fortran coders I talk to, so those say in senior level positions, so those that still have their TI-35 on the desk, they see two solutions to the problem solved with those views. One solution is, well, just do everything in one dimension. You don't need all this. The multidimensional stuff is only in your mind. In memory, everything is flat. And the second solution is functional autism. So usually our users don't have either of those. So, well, how to convince them? Yeah, well, you need benchmarks. So now I have to switch to my console, which is always quite an experiment with PowerPoint. So let's see if I'm to the left or to the right. Here we go. No, that's not quite. Is that legible? I'll just detach and reattach, perhaps. So that should be better. Come on. No? Thank you. Okay. And now back here. Okay, doesn't like me, but whatever. So let's see what we get. I have builds with several compilers. I just picked the most drastic one. So MPI run usually starts distributed processes. So this is running on my local laptop, but it will still run a process on a pinned core. And this is called bench 05 array range. So what it does is it just compares this lengthy code that is state-of-the-art that exposes state-of-the-art performance. So you wouldn't. It's not drastically efficient, but you also wouldn't soil yourself publicly. And then we compare it with this nice 3 lines view expression that has everything with bells and whistles and see what we get. So this is compiled with the vanilla GCC 5.4. And so when you divide GUPS, so this is to say giga updates per second, so how many indices per second can you dereference, and then you divide the one by the other, and then you get the speed up. This is how many times views are faster. So about stable 7 times. Any idea why that is? Those familiar with the ranges proposal perhaps have an idea. So when you look at this, the implementation of this index set sub, what it actually does, there's one operation that is a one-liner. Compilers love one-liners. And especially when you write some const exp before and when the type is totally clear and then you just throw it into Compiler Explorer and you see that it's just one L sub or whatever. So there's not even a function call. Yes?
Does it work on, like, do you express the values you work upon in your program, or is it like you feed them out from the outside?
Say that again?
Can you, okay, so is this working on constants known to the compiler, or is it working on values loaded dynamically?
No, the sub range is defined at runtime. But what exactly happens there? So you have this local part, which is a way more complicated arithmetic expression, or algebraic expression, I should say, because it has variables in it. But at the end, you have one arithmetic expression that actually translates to the index calculation. And when you have those views with just as I've shown before, with all those one-liners and const exp and nice inlining and return value optimization and whatnot, what the compiler actually produces is a single arithmetic expression that is constant folded, and everything that's left is to fill in this begin and end, and everything else is folded. So yeah, perfect question. Yes, so if it would just work with constant ranges, it would be pretty boring. But it's also interesting. So when you pass const exp ranges, so const begin, const end, it just folds to a compile time value. Why don't I have a demo for that? That would be cool. Okay, let's see if I can switch back. Okay. Yeah, and this is the reaction we usually get. And when you travel a bit and show this to many people, then at some point they grasp it and say, okay, but this is C++, you say. And the problem is really what I had before. At the bottom right, I saw some C++ in 1998, and it looked like an 80AP power of plan calcul. It's not exactly a quote, but it's close enough. So in the last grill the community, there was a term coined black matter coders. So black matter coders are those that looked at a C++ book, not the good one, and learned it and said, okay, this is from henceforth I will allocate memory like this. And I shall never mix alloc and new, and I shall never mix free and delete, and no one ever told them you shouldn't mix them because you should only use one of those, and actually also those you shouldn't use. So those are black matter coders, and this is actually the biggest, the most difficult hurdle in convincing users that this is a good idea. The mathematical part is not a problem. So those are some expressions you can pipe. On the left, you have begin, end, size, rank. So rank would yield the active number of dimensions. There's also ndim, Who knows the difference between rank and number of dimensions? We can talk later. Then you have domain and origin. So domain would just go one step back in your mapping. So if you have sub local, it would just go back to the last sub. Origin goes back to the last owner. So what if I say array local sub, and then I call origin on that? What's the origin? Well, it's array local, because the array local is an owner. It's the owner of the local data. And if you have array sub and called origin, it would return to the global array. So just depending on which index space you are. Then we have operations like join, stride, chunk, sub, expand, and shift. Those are crazy. And we have some predicates, like is local, is contiguous, is global. And also those predicates are evaluated at compile time mostly, which is really useful. And of course, we have view traits, because otherwise all this constant folding in SVNI wouldn't work. And the views and index sets are again based on those view traits, just to know where exactly in the chain they actually are. So when you remember the template arguments passed in, I just swap back real quick. Where's the code? Here we, nope, sorry. Here we go. So when we look at the template arguments, so in every view type, the domain, the type of the view's domain is included in the template parameters. So when you have sub, local, sub, it would be a pretty lengthy type. And this is why modern C++ is awesome, and why we only could ever use this with C++ 11 and forward, because otherwise you would have to state those view types explicitly, and those span easily over four lines. So Hindley, Milner, Otto, thank you very much. Okay. So we were talking about, here we go. So all that stuff that I explained, this basic principle, you have an index set, and the actual operations are on the index set, and views just reference any index set they don't actually have any idea of. This can be applied to just any library, like, for example, Blaze, or HPX, or so it doesn't really depend on Dash at all. Dash is just a really nice example, because we have all those cerebral coital index spaces. So this was all one-dimensional, and there's one expression that you probably can't make much sense of. This is pattern. What is a pattern? Well, once you have multiple dimensions, you actually have to you have exponentially more possibilities to distribute your data in your one-dimensional cluster. What does that look like? So in one dimension, it's pretty easy. You have those chunks, and then you could say, okay, I have a chunk size of 20, and I deal them to the units like from a deck of cards, or I balance them, so every unit has exactly one chunk. In 2 dimensions, things get really, really awkward. So we consider the multidimensional partitioning and domain decomposition as a mapping in 3 stages, which is static. So you have a static container like a 2-dimensional array. So there is -n array that is capable of multiple dimensions. And the pattern is static. And a pattern has 3 mappings in the categories partitioning, process mapping, and memory layout. So first, we have the global canonical domain. Then we partition it into blocks. Then we deal those blocks to processes. And when you linearize the index space and all the units assigned processes, you have the local memory layout. And this is static. So for example, this element, global 26, well, should have put it to the top. So the global index 26 maps to the global block 5, 0, 1, 2, 3, 4, 5. And in this, it's the element at offset 2, 0, 1, 2. Block 5 again maps to unit 2, block 1, so 0, 1. And in this, it is at offset 2, 1, 2. And this again translates to unit 2 offset, local offset 6. Are we having fun yet? So this is the mappings that the pattern concept provides. And of course, there's lots of unthinkable multitude of partitioning schemes. So there's a paper in the Dash ecosphere that is pretty much a literature review of domain decompositions used out there in the wild. And I identified a nomenclature for properties they have. Any idea why I would want that? So, for example, I don't communicate patterns in terms of type names, because what exactly is your association with a sequential tiled balance pattern? None. You would just look it up in Doxygen and look it up every time you need it. And you would never know that there is, since version 2.0, there's a way better pattern for your use case, and this is all horrible. So what I do, I document a classification of properties in those three categories: partitioning, mapping, and memory layout. And the types can be deduced. So when you implement a distribution scheme, you just annotate it with property tags, like with an iterator. So like forward iterator, random access iterator, the same. That's the same we would do here. Just as an example, when you just change the mapping property, so all properties stay the same, and I just take the mapping property as a degree of freedom and change the properties a bit, so the defined tags. This is a neighbor unbalanced pattern. Why is it unbalanced? Because not every unit has the same amount of blocks. So unit 0 would have one additional block. It's a neighbor pattern because adjacent blocks would never be assigned to the same unit. This is neighbor unbalanced, so you need one additional unit, otherwise you couldn't balance those blocks out. Isn't that a nice implication? That's a prime example of read the fucking manual, right? So yeah, of course you can't instantiate it, of course it will fail. Your dimensions aren't balanced. And of course it's got like 100 ups on Stack Overflow. And then you have diagonal balance, which does exactly the same, but is optimized for diagonal sweeps. Nice. So yeah, what we do is we have a make pattern. You feed it the properties you actually need, and then you get a proposition for the template type. Is this well defined? No, of course it's not. There will be, it could be that 2 or 3 pattern types or instantiations match the properties you requested. But just give it a try, it won't be wrong. At least it will compile, it will run, and it will be semantically stable. And if the performance is an issue, then you will have a look at our traces. And another thing we desperately need, or we already provide, is a visualizer. So you can just run. It's called pattern block visualizer, and you feed it. You feed it with a partitioning configuration, and have a look at it and see if it's what you want. A student of mine is currently working on an interactive variant of this, so you can just open it up in the browser. So you just yield pattern visualize, and it will communicate back to. Just play around with it without even having access to the machine, which is pretty nice because this installation that we publicly provide will always run on the most recent version of that. Yeah, right? That's what I told my student, but some other time. But and also it's a bachelor's thesis, so come on. Okay. So what are our special needs? So okay, so this is complicated, and it's even if you are a highly functional autist, you still have no way of knowing which if there is a better partitioning configuration for your use case, or if it's changed in the next release, etc. It's pretty horrible. But what we want to provide is, well, the same as the STL. So the STL doesn't actually have multidimensional containers for good reasons. We are allowed to specify multidimensional containers because we are domain specific, because it's for HPC. So we do. So what we want to provide is, well, we want a multidimensional range should still behave like a range if needed. So you can say matrix begin, matrix end, and it would iterate in the canonical fashion. The canonical fashion is this one. the one you would expect. The distribution underneath could change. So for example, I have a tiled distribution. It would look like this. And this is the local index set, the local index part you would get. So mat local would give this index. And those have different iteration order locally. So you have the canonical order that never changes, no matter which distribution scheme you have. And the local storage order just depends on memory order. So why all the hassle? Why do we need this canonical order? Why not just say, yeah, well, iteration order is local order. Be done with it. Yeah, well, because you have to optimize or specialize your algorithms for this specific pattern, and that's horrible. So if you have, for example, a strided distribution scheme, then the algorithm would have to detect that at compile time or whatever, and this is all horrible. We just want to say begin end. We have ranges, and they can be multidimensional. So, for example, how about we have a two-dimensional matrix in that, and we run standard copy on it. Standard copy has no idea of, as we had before, it has no idea of domain decomposition, no idea of multidimensional stuff. All it knows is, well, there is an iterator, and I just go on until I meet my end, or until the not equals predicate yields. And this would work. This would exactly return what you expect. And it would be horribly slow, of course. So important part is the actual achievement in this, even if it sucks. It would always yield the same outcome for any for any distribution scheme you run underneath. Because there's views in between and patterns that are static, and static doesn't that sound already like you could optimize or run it at compile time? And indeed, most of the static pattern mappings are really easy to fold. So a dash copy gives the same result as standard copy on a matrix. And coincidentally, so a dash copy on a regular standard vector also gives the same result because we comply to STL concepts. So what we learned is what algorithms have to do. Algorithms always communicate to the application or to the user a canonical iteration order or a canonical multidimensional arrangement. So you can, for example, you can iterate it in a range fashion, so in a one-dimensional index, or you can have multi-component indices like column and row. And underneath, it would have to sort out where exactly the indices are. So a dash copy for this distribution would have a totally different implementation than a dash copy on this or on this. And you don't have to care because it's, of course, most of it is decided at compile time because we have pattern properties. So dash copy has a reference to the iterator that again can publish the pattern properties of the matrix, so you can deduce it at compile time. So for example, we take a two-dimensional rectangle. The operation for this, or the expression for this, is sub. Sub is nice. So from those in category theory, you know why. So sub could be a sub-range, a sub-rectangle, a subspace, a subset. So yeah, whatever, sub. So it's not subtract because that would be diff. And so I just said, okay, we communicate a canonical iteration scheme to the user, to the application. So that's what the application does. This is how the data is distributed. And now let's be nasty. So okay, I want this rectangle, totally ignoring alignment of distribution. And now I want the local part of that. And now I want the indices from that. And then I want to know if those are contiguous. He said and opened the console. Okay, let's see. So what I will do, I will split this view. No. Thank you. Okay. And this is called x2. Let's start easy. Okay. Sorry. I forgot the reason why I was splitting. Here we go. Sorry. The other way around. Here we go. Ah, finally. Okay. So at the top, this is the original matrix, just for reference. And decomposition scheme that you come up with. So the default is just tile. So it's a sequential tile pattern. And you already have no idea what a sequential tile pattern is, because it's way easier to just communicate with properties. Okay, so this is the global matrix. Then we apply. Oh, I should have filtered those out. I'm sorry. Here we go. Where's my mouse? No mouse for me. Here we go. So this is, for example, matrix begin 11 to 20. So one-dimensional subrange, and it gives 11, which is over here. So the number before the decimal point, this is the unit ID. After the decimal point, the decimal places are the local offset at the unit. So you have 0001. Yeah, exactly 0001, 02, 03, and the white numbers to the left. This is the canonical index. So 0, 1, 2, 3, 4, 5, etc. And locally, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So then we run matrix begin. So I want a subrange, a linear subrange from index 11 to 20. So it starts over here. I just picked this one because those at the border are the really nasty ones because of by ones, you know. And we go to 20, which is over here. So 20 is 005, and this should be 005 exactly. Well, there's one good thing that I forgot to remove the type dumps. You see the actual sequence of the type that is produced from just this expression. Okay, next one. Matrix local for unit. So at the left, this is the unit. Matrix local for unit 1 would be canonically 0, 1, 2, 3, 4, 5 to 11. In the unit range 0, 1, 2, 3, 4, 5, 6, 7, etc. Okay. And this is the same for all the other units. And then I can access blocks. So blocks would just partition, arrange into the blocks you saw before, those colored rectangles, which is a contiguous chunk in local memory. And this is, for example, relevant for a dash copy, because you always want to copy a contiguous chunk in local memory, not stride, whatever. So the first block in local memory of unit 1 is global index 0 to 6. 0 and 6, sorry. So this would be here, 0, 6. And no, this is wrong. Because I'm in local index range, I'm sorry. So this is a local index, of course, because I applied local to it. So it's 0 and 6 in local memory of unit of unit 1. That should be fine, because it's the same for unit 0. And you can chain those. And just this expression, I want the I have a subrange, I want the local part and the first block from that, or iterate over the blocks in this range. So this is where even the TI-35 has its limits. But we can get drastically more evil. Whoops. Okay, so this is the image that you can keep in your mind. We have at the left, this is what the application sees. And at the right, this is what's actually allocated on the machine. And everything in between, this is index operations and views, and everything you don't have to care about, because you only use those view expressions. You have an algebra on those index sets. I said the evil about algebra. So yes, there's morphisms and lots of morphisms in that. We can talk about this later. Call me. Let's be nasty. So let's take a block right from the matrix, the global memory space. Then I want to expand it. Why would I want to expand a block? Hey, remember those halo cells in the beginning? Yeah, really useful. And then I want to shift it. Come on, shift. Thank you. And I said shift by 2, shift by offset 2 in dimension 1, but it only did 1. So what does it do? It reduced the size at the right. Yes, because the index range is limited there. So you can't do anything wrong. You don't have to bounce check. A view expression will never return. Yes, currently it will because it's buggy. But conceptually, a view expression will never leave you with the burden of bounce checking. So what happens if you just shift it all the way out of the matrix? Yeah, well, you get an empty view then. But it's still perfectly fine. You will never have never have a situation where you have to get an index just to see if it's within a specific boundary. You can do that. You can access the index. You just pipe index and you get the index set. Sure, but you don't have to. Yep.
That's good, like conceptually, like slicing in other languages, like Python or like.
It's way better.
No, I know, but
like
conceptually, like it gives you back like a list, like a set.
Yeah, slicing is a true subset of view expressions. Yes. No, yeah, but you're absolutely right. Yes, but what slicing does is there also is XX. It's a library XX. Yes, but in C++ and more general. Tensor, xtensor. Exactly, xtensor, that's a C++ library, really well done. And you can present it with a one-dimensional range and say, you know, reshape it in 2 dimensions with base dimension 4 or something, so base extent 4. But what they do is they just wrap it with an iterator that will just stride every 4 elements. It will stride 4 elements or something. So this is conceptually, they're doing the same. They have an index set, and the iterator just walks through all the elements in the index set. But this is way more drastic because we have lots of different index spaces. Okay, so this looks nasty. Let's see what we can do. Okay. So this time I shouldn't have any log output. But I have to guess which one of those demos it was. But it didn't have a segfault yet, so let's use subviews. Subviews is pretty harmless, I would say. Come on. Here we go. Yep, it just come on, where is it? Here we go. I will have to reduce the font size a wee bit, or I'll just use fewer units. I think that will do. Come on. Let's use 3. Oh, that's better. Okay, that's our matrix. I again did it completely wrong. Sorry. Sub and 3 units. Here we go. So that's the original matrix as before. This is a slightly different domain decomposition scheme, but we don't have to care because we use views. So in this case, I take this nasty subrectangle, which is from global index 25 to 42, right, about here, right? So, and as you see, global index space is preserved. Now, let's be nasty. Now I want the blocks from this. And here you can see this because it's, I'll just go up a bit. So the first block from this sub-range, which starts, where is it? Here. 25 is our first. I'll just mark the range again up here. 25 to about here. Sorry. This is something Tmux doesn't solve yet. Okay. So from this subrange, I have the first block, which yields 25. Why doesn't it give 17? Why doesn't it give 16, 17, 24, 25? Because that's not what you want. You always have a well-defined subset. You always have a so-called topology. And this is one of those predicates So I just ask it, is this block contiguous or remote? In this case, yes, this block is contiguous, trivially because it's one element, and it's remote. Why? Because this is from the perspective of unit 0, and this is allocated at unit 1, so it's a remote block. This is contiguous and remote. This is contiguous and local. 28, 29. Let's see if this... So this one is strided and remote. Yeah, sure, because 23, 41 is strided. There's some elements in between. You see it even better here, actually, because the global range is irrelevant, but there's the 10 missing here. So this is contiguous and local. It's a full block. Yeah, sure, 12, 13, 14, 15. So when you look back at this dash copy, you see why this is useful. I just can apply a local filter to it, and now, okay, this is my local block. And then I apply a local filter to my target, and then I do a standard copy from that, and I'm done. So at least for the local part. Okay, this is pretty nasty, but I promised halos. I promised even more drastic stuff. Let's see. I don't know how many units to use. I think 3 will be okay. Can't you see it?
You always did it in the first one before, and then you moved it down.
It's because I'm an idiot. Thank you. I still look like an idiot, but at least now we save some time. Halo. No, this is boring. We can do it, but it's really boring. Let's use... What's nasty? What's really nasty? Yeah, it has to fit on the screen. Okay. I am so... yeah, my usual setup is the other way around, sorry. You know, I'm not used to think in multiple dimensions. Yeah, that's better. Okay, this is the original. Okay, again, bit different allocation scheme. Okay, so we have blocks 0, which has offsets 0, 0, and extends to 2. This is again offset and extend are also view expressions. Then we expand. So I expand in every dimension by 1 extent. But it didn't expand to the top and to the left because there is nothing to expand. And then I shift the elements in this range by 1 in this direction. So now I have there was 0, 1, 2, 6, 7, 8, and now it's 1, 2, 3, 7, 8, 9. Global index is preserved, local index is preserved. Overhead close to none, because I specified this offset at compile time. And halos, well, usually you know how many halo cells you need from your neighbors, so you can specify at compile time. Because this cross, this 5-point stencil, as we call it, that's usually known at compile time. So this is really, really zero cost abstraction. And then is there a really nasty block? So yeah, so we take this block. This is 2, 3, so it's this one. We expand it, we shift by 1, etc. And then we take the first block from it. The first block would be this yellow area. Yeah, and from that point on, I hope you believe me that it just works. Now this one is interesting because, oh no, I have to scroll up a bit. So this is nasty. Well, this is just 1, and of course I can ask the block range in this case: are you contiguous? Are you local? What's your extrema? Yeah, and yeah. It's the same.
It's the same?
The ghost cells are halo cell viewed from the other side.
But don't you typically have like a local copy of these things and then the bulk communication?
Exactly. Absolutely. That's what the slide in the beginning was all about.
Okay, so essentially you have a local copy that you're accessing there.
What does it? Okay. I was already on my last slide, so I can. This is a good point to step back. Just have to find it. Here we go. Oh, that's the stencil. Exactly. So that's what I wanted to illustrate by this dashed line, that you have a copy of the remote elements in the address space of the local process of process A. So you copy it in a chunk and then you access the copy. And you have a back and a front buffer, and so you know those values won't change in the current iteration, yada yada.
So what is, how do you treat that programmatically? Because essentially access to these cells is comparatively cheap.
To the once it's copied.
Compared to completely remote cells. So if you write an algorithm, I feel it is somewhat.
Yeah, exactly. When you write an algorithm like that, and so if you just want to do that, because HPC application programmers don't want to do that or this; they want to do that. And when you just you could just use the stencil on the dash matrix, and it would just suck. So you of course have to optimize it for this halo exchange. And instead of calculating all these indices by hand, like this 0 mapping to 0, 1 to 8, 2 to 16, etc., you just say, I have a local block, I expand it. So you can specify a wraparound, and you can specify an overflow. So you just expand it and copy from there, and then you can ask if it's threaded, and if it is, then you use a threaded copy, otherwise, etc. Yep.
How does that like work with update policies?
That's orthogonal. They don't interfere at all. That all the views, all views do is just give you, a representation of a contiguous range, and then tell you whether it's contiguous or not. But update policy, that's what the algorithm does once it uses the views. So when so with plain old C and MPI, you would just allocate this local buffer and calculate the indices, do a strided MPI copy, etc.
But like based on the size of your extent, for example, you have a different you need to check. Like, do you do like rep counting, or like how do you do it?
That's the problem of the algorithm.
So that's just like as an application program, you don't care.
Yeah,
That's the backup.
exactly.
Some customization.
No, views have no idea views actually have no idea of ownership, other than that they can translate between index spaces, like those local unit index spaces, and those imply ownership, but indices and views have no idea of that. So no, it just replaces your index calculations and off-by-one checks. Yep.
Actually, what would be a real-world example where you have such a huge amount of data, distributed on our systems, that is mutable?
That is?
That is mutable, that you can, but a real-world example, not this is a fabricated one, or so that
Why shouldn't the data be? Well, there's two things you can do with data. You can, or three. You can access it, you can compute it, and you can use it. If you don't do the latter, then the first two are pretty much.
But you can use it. Of course, you can read it, but you don't need to update it.
Well, it's like
what would be a use case where you really have a lot of data that you also want to update?
Let's say for example, you know the Gaussian blur filter in Photoshop.
And you want to
apply that on a 4 terabyte image.
To replace the image in place, to modify the image in place. This will be the.
It doesn't actually. That. Yeah, you could leave the original image in the const and just operate on a result buffer. But then the result buffer would be mutable, so you didn't gain anything from that, because you still have data that has to be updated. Because so you run this stencil isn't run once; it is run like 100 times from the beginning to end.
Yeah.
And yeah, so there will always.
The question is actually very simple, because if you don't have any writes, any updates, then you don't need to synchronize access.
Oh, of course, yes. But views don't know about that.
Exactly. So actually, the part with updating this huge data, it's a completely separated problem. So
exactly.
You can ignore it first. Let's say,
exactly.
Let's put it like that.
Views are just so the benefit of views is that they support the implementation of algorithms, like for example this. Why didn't it? Sorry. Jump to the wrong slide.
What is actually the follow-up of that is that if your updates are seldom,
here we go,
or you don't have them, then you can replicate data.
Sure. But that's orthogonal to views. So the idea of views is that they support the implementation of algorithms, like this dash for each, for example. But the overall procedure of the algorithm doesn't change at all. It just simplifies all those index calculations. And also, you don't only have to implement one variant of the algorithm, because everything that is another word for multivariate, that anything that depends on the domain decomposition underneath, that is cared for in the views. But the update policy and also memory model and and communication schemes, views have no idea of that. Views are a really, really mathematical concept. And there is one programming language that is really good to abstract those, and that's of course Haskell, but C++ is going there. And so as far as views are concerned, C++ achieves Haskell abstraction. We still need concepts, like really. Yeah?
Just to clarify, so the ghost cells, they are copied by the algorithm that you call.
Exactly.
Yeah, okay.
So I should have added another slide to illustrate, perhaps. Where is it? Here we go. Yes, so this process A, the idea is to reduce the communication issue by process A. So process A copies the remote range, because he will need the data later. And likewise, process B will copy the east boundary of process A. Yep. There's a whole paper on it. Do you want to see it?
The paper implementation, like the same thing.
Oh, the implementation. That is the implementation is not based on views yet, because I didn't merge views into development yet. Do you want to have a look at the Summa implementation? So there's one thing I did wrong when I started to abstract all these index and view stuff, and that is I didn't free my functions. So in the beginning, this is like 1.5 years ago, you didn't say matrix pipe sub, you would say matrix dot sub. So you all know why this is a bad thing, right? We all know, we don't have to mention it, no. So I can show the implementation of matrix multiplication, which actually owns MKL and ScalaPack and Plasma on like 4 machines. Thank you. So it's not. So I will give you the raw, unabbreviated. Okay, you asked for it. Code dump. Come on. So this the algorithm is called Summa, which is really a specific algorithm, but it's alias to -mmult. And sorry, my Vim is booting. The nice thing is when you when the matrices A, B, and C, so C equals A times B, are pre-allocated, then this algorithm will determine the communication scheme from the existing partitioning. And you can go the other way around, and before allocating the matrices, you can say make pattern with the Summa partitioning constraints. So you say, I want to apply Summa to those matrices. Just give me a partitioning for matrices A, B, and C such that Summa is optimal. So anyone experienced with ScalaPack? Okay, take my advice. Don't change that. Well, there's in the benchmark for this algorithm, there is of course a ScalaPack variant. I can show you. You will see. So okay, this is ML local. This is all internal. Boring, boring, boring. So those are the optimal partitioning properties for the Summa algorithm. So we have those categories: mapping, layout, and what else? Where is it? Mapping, layout, and here we go, partitioning. And so when you say make pattern for Summa, then you will get this configuration. So either you tell Dash what kind of algorithm you want to run, so specific algorithm, or you already have pre-allocated data from an external library perhaps, and a dash has the other a degree of freedom and has to determine a correct algorithm for that. So there's a summa, matrix type A, B, and C. I do not use iterator ranges for that because we are mimicking a dgem. And then there's lots of. So do we have a shifted tiling? Do we have a minimal tiling? This is all compile time stuff. Then, if those constraints are not met, then throw. If those constraints are not met, we can't determine this at runtime, at compile time, because the extents can be specified at runtime possibly. If it's a shifted tiling, if it's a minimal tiling, this is just logging stuff. Then we assert some more. This is all for the compile time. Here we go. Where is the block? So we mkl-malloc it. Yes, this is the local buffers. Finally, here, this is the old variant. This is matrix C, local block 0. Now we would write C pipe local pipe block 0. Semantics are the same. But, well, with the new variant, so with pipes something, you don't have to reinvent it for every goddamn container you implement. So what exactly does the container have to specify? The container has to publish its pattern, which the static distribution scheme with all those properties, and a global memory reference. Global memory reference is pretty much something that malloc has internally. So it would return the local physical address of the current unit and MPI offsets of all the other ones. So it's pretty much the an equivalent of the malloc runtime and the pattern. So, and then of course you can from this block you can have a begin, and from this you can get the view spec. A view spec is just a struct with extents and offsets, and this is now pipe extents, pipe offsets. But here I calculate both because it's cheaper if you need both of them to calculate them in one iteration. So yet another advantage when you use free functions. And this is the summa algorithm. Summa algorithm is actually pretty unsurprising. It's just a blockwise matrix multiplication. And there is one scheme where matrix A is distributed in a row major fashion, so row-wise, and matrix B column-wise, and then you can calculate an element with local data at least once. And we just measured that for remote. So for RDMA, so for one-sided access, there is no advantage in doing so for Dash. Of course, we have futures. So we use, where is it? Block A begin.local. Oh yes, you can convert an iterator to a physical address if you know that it's local. You can still do this with pipe expressions. You just say array.begin pipe local, then you get a local address. Yep. Okay. No, I'm just telling wartime stories. So, but you get the idea. So this algorithm will have to be rewritten, or not rewritten, but reformulated using the new view expressions once we're done. Any other questions?
How would I implement the game of that? So would I just
that's a programming course exercise actually. So you can download it from the parallel programming course workshop. It's a great example. It's my favorite example for stencil. Yes. It depends. So you have a stencil that is distributed in two-dimensional blocked fashion like before. Why would you need two views? So you have a back and a front buffer.
Yes.
Exactly, yes. Yeah, sure. But that's just the regular non-distributed game of life version. You will always need a back and a front buffer.
Maybe there's a real question behind this question.
Do I need a view for each buffer, or can I use one?
Yeah, you need you will have of course you have a different view because they reference different containers. But the view expression would be the same. What you can do is you can formulate the view expression that would be the same for all views and save it to an auto, and then apply it to different containers. Oops, sorry.
Views are cheap.
Views are really, really cheap. So when I just remove one const expr, this all for the whole card house pretty much collapses. But yeah, if forwarding and moving is done correctly, then views are really cheap. But that's my problem, not yours.
But not done correctly, your library working on really tries to use, some people would say, abuse
Yes.
information about a certain kind of architecture. You have heterogeneous execution, so maybe one machine has some kind of simple instructions, another one doesn't even have threads in a certain kind of context.
So you need another. Okay.
So who defines the information? Is that static or runtime?
You can read it in my PhD thesis once it's ready. Yeah, because that's a fabulous final question, because that's exactly the topic of my PhD thesis. So once you have this high-level abstraction and index set and post set semantics and whatnot, which is actually, this is a really slim chapter in my thesis, because as we all know, post set semantics are defined such that the implementation in C++ is scientifically not that important, so I'm glad I can tell it here. But you're perfectly right. You need another layer of abstraction that pretty much decides dynamically, or at compile time, once the machine information is available, what kind of, for example, partitioning strategy or index recalculation you need. But that's again not a problem of the views, because views just know about Cartesian index sets.
So Dash has a solution already? Do you know one in your head?
There is a Dash library, a spin-off called Dialog. Does anyone know HWlog, hardware locality by OpenMPI? Cheater. Anyone that's not my student? Okay. So yes, we have a library that is exactly delivering machine information at runtime, and I try to bring those two together. So at the end, you just write your mathematical definitions or declarative variant of your algorithm, and it just adapts to the machine at runtime even, once I finish it.
How do you do that, like from a compiler perspective, for example, like alignment or like,
No.
like the instruction you produce?
We are pretty much over the time, aren't we? Because I'd like to answer that question, but perhaps you should do it outside while I'm having a smoke or something.
Not fair.
No. I could. What was that?
From a location point of view.
Yeah. So I can answer your question like for hours and days, but not in this room. Okay.